Hey guys, welcome to chapter 3. And in chapter 3, we're going to be looking at exponential functions and logarithms. So to start, we are just going to start looking at what it means to be an exponential function. So if you look at these two examples here first, we've got f of x equals 2 to the x. If you notice, the x is in the exponent, which makes it exponential. And if you notice the second one, you got 0.6 to the x, which is an exponential function. So all we're going to do on this first slide here is very simple. We're going to practice knowing how to do it on a calculator. How do we actually put in a exponent into the calculator? So if we have f of x equals 2 to the x power, if I want to know when x equals negative 3.1, all I'm going to do is I'm going to say what is 2 to the negative 3.1 power. And just a reminder on how to do that on your calculator. You have 2, you do the little caret button, and then negative 3.1. If you hit enter, you should get 0.117. So f of x, when we put in negative 3.1, is going to be 0.117. And notice in the directions it asks you to round your answer to 3 decimal places. And then just again another example where we have some fractions and decimals that we're dealing with. You're going to put in your calculator 0.6, and then you're going to hit your little caret. If you want to have an actual fraction, so it looks like this, remember that's your alpha, and then the button right next to it, I think it has the X on it, and right above it, it has that little picture in green. That's how you're going to get the fraction. Otherwise, you can just do 3 divided by 2 and have 3 halves. And when you put that in your calculator, you should get 0.465. So g of x in this case is going to equal 0.465. Again, just a little practice with our calculator. Okay, next we're going to start looking at some graphs, and we're just doing sketches here. We're going to use our graphing calculator, things like that, to find the information that we need and what a exponential graph actually looks like. We've, I think, looked at some of these maybe in the previous chapter, but we'll remind ourselves. One of the things about exponential functions is that they have asymptotes, and an asymptote is just a line that a graph approaches but never actually touches. So if we're looking at exponentials, we are going to have a horizontal asymptote, and remember, a horizontal line is always in the form of y equals a number. Okay, if it was a vertical line, it'd be x equals a number. So we're always going to have a horizontal asymptote here, where it's going to be y equals whatever value that graph gets closer to, but never actually touches. So let's just look at a couple of examples here, and we can use our graphing calculators to get an idea of what it looks like. And then the other thing, really the main points you need to know is where the y-intercept is, and then looking at your graph, you should be able to tell where the asymptote is as well. So if we look at f of x equals 2 to the x, so if you want to pause the video, take a second, put it in your graphing calculator, you should end up at a graph that crosses, make this a little bit smaller, there we go, that crosses the y-axis, or y-intercept at 0, 1. And it looks like this, where it is very close to our x-axis, and then it shoots up just like that. And even if you expand your graph out and things like that, that graph will never cross the x-axis. So we actually have this, what's called a horizontal asymptote at y equals 0. So if we think about why that is, right? Let's think about logically here for just a second. If y equals anything less than 0, right? So that horizontal asymptote says it gets closer and closer and closer to y equals 0, but never goes below it. Well, what that means is we would never have a negative value. It's not possible to have a negative value. So thinking just a little thought bubble over here. Okay, here I'm going to have my little thought bubble, right? If I have it asking myself, let's say negative 2. Is it possible to take positive 2 to a power and end up at negative 2? Right? So if we take 2 to any positive number, 2 to the first is 2, 2 to the second is 4. Even if we take 2 to a negative number, 2 to the negative 1 is 1/2. That just moves it into the bottom. There's no possible way, even if we had -3 equals 2 to the x, there's not a possible way to take a positive number like 2 to a power and end up with a negative number. So we are not going to actually have any value, that y value could never actually be less than 0. So that's what our asymptote is actually showing us in the graph. And if we're talking domain and range, again, we're going to use interval notation to express that. Domain, remember, is how wide the graph is. It's your x's. And range is your y values. Okay, so our x values, if you read left to right, left to right, we would start at -infinity. And if you look, this graph, as it goes up, it continues to go to the right, so it's going to go to positive infinity. Let me erase a little bit of that. Okay, if we are looking at range, our range is our y values, and we read range from the bottom to the top. So if we start on the bottom and we move up, the first place that we see any of our graph is at 0, but it doesn't include 0. Remember, it can't ever actually touch 0. And then it keeps going on up, 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 up to infinity. Okay, so let's just look at a couple more where there's a little bit more going on with the graphs. Here we have 4 to the x minus 3. So if we take a minute, pause the video, put that into your graphing calculator, what you're going to find is we want to make sure we know where it crosses the y-axis. So it crosses, if you look at -2, and it looks a lot like this, where it's coming, skirting right along there, and then it shoots up. That might not be exactly right, but if you notice, looking at the graph, as it in this area here, it gets closer and closer and closer and closer to y equals -3, but it never actually crosses y equals -3. It gets closer and closer, but never actually goes there, which means our horizontal asymptote is going to be y equals -3. Our domain, again, goes in both directions, so our domain is going to be -infinity to positive infinity. And our range, again, our smallest value for our graph is at -3, and then it goes up to infinity. Okay, so that one, if you notice, there's a -3 on the outside, and it moved the graph down 3 units, which we've talked about that. It's the same with the exponential as it was with quadratics. So we have, again, now I've just changed the base to 8, so you have 8 to the -x plus 5. Just make sure when you're putting this in your calculator, the -x plus 5 stays up in the exponent. And what you find is that this negative is going to make your graph look a little bit different, and this 5 is going to move your graph to the right 5 units. Okay, so what your graph is going to look like is, let's see here, something a little bit like this. And our y-intercept here, in this case, is going to be a very large number. So I'm not going to worry about the y-intercept, but you could find it on your calculator. So our horizontal asymptote, if you look, this part of the graph here keeps going and it approaches 0. It gets closer and closer and closer to that x-axis, but it never actually crosses it. So our horizontal asymptote would be here at y equals 0. And then our domain, again, it's going in both directions, so our domain is -infinity to positive infinity. And our range, it starts at 0 on the bottom, and it goes to positive infinity. Okay, so then some other things is a very basic look. We are going to look way more at exponential functions and logarithmic functions and solving with them, but a very basic way to solve with exponential equations is what the textbook calls one-to-one solving. Okay, what that means is if the bases are the same, the exponents are the same. So if you can get the bases to be the same, that means the exponents will also be the same. So if I'm looking here, my base right now is a 9, and I've got a base of 3. So my base over here, let's see here, is a 9. My base over here is a 3. I need both of my bases to be the same. So I need to ask myself, well, how do I write 9 so that it is a base of 3? I can just rewrite it as 3 squared. And then over here I have 3 to the x plus 1. Notice what I am not doing. I am not saying 9 equals 3 squared to the x plus 1. Okay, and calling that 9 equals 9 to the x plus 1 or something like that. Kids like to do that quite often. They like to try to change the smaller number to match the bigger number. But in this case, if our bases are going to be the same, this has not changed. The way I have it written here has not changed at all. 3 squared is still 9. 3 to the x plus 1 is still 3 to the x plus 1. Okay, so we don't want to start trying to change too many things in there. We need to make this equation is still written the exact same numbers and things. It's just we manipulated it a little bit to get it so that we can do what we want to do. And then once we know that our bases are the same, that just means that our exponents are the same also. So that would mean that 2, oops, I need to do a pen there, 2 would equal x plus 1. And if I subtracted 1 from both sides, I would get x equals 1. So bases are the same. You can set the exponents equal to each other. Okay, the next one is we've got a half and we've got 8. So I gave you a little hint over here. I said, what is the relationship between 2 and 8 exponentially? Okay, so if we think about that, 2 to the third power is 8, right? But we don't want 2, we want 1/2. So thinking back to our exponent rules, right? If I have 2 to the negative first, that's the same as 1/2. Okay, so if I have something, thinking about that a little bit backwards from where we had before, right? I know that 2 to the third is 8, and I know I've got a 2 here, and I know I've got an 8 here. That means I can rewrite it. Let's think here. I can rewrite 1/2 to the x equals 2 to the third. Okay, well, I still don't have matching bases, right? Because I have a half and I've got a 2. However, I can say 1/2 x to the x equals 1/2 to the negative 3, right? Because by going from a positive exponent here to a negative exponent, that just flips to the reciprocal, which means now I have the same base. So I've got a half and a half, which means that x equals negative 3. Okay, so our next idea, and this is the first section of the chapter, so there's a lot of things in here that they introduce in the first section that you will be using for the rest of the chapter. So as we move forward through the sections, these are things that are going to keep coming back that you're going to have to use. So one of the ideas that we're going to continue to use throughout this chapter is the idea of base E. Okay, so base E basically is just kind of like, E is like pi. Like pi is 3.14, blah, 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 goes on forever and ever and ever. Euler's constant, 2.718281828. It keeps going on and repeating forever and ever. So instead of using that big decimal, they just use E. Okay, kind of like instead of using 3.14, blah, 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 we just use the simple pi. Exact same idea. E has a numerical value, just like pi has a numerical value. So if you want to take a second to find E on your calculator, it's found by pressing the second and ln. Okay, so right below where it says log, you have ln. Right above ln on your calculator, it says e to the x. And anytime we use e, we're going to have an exponent that goes with it. So here are some practical ways that you actually can use a base of e. And we quite often use these examples for base e and exponential functions because it's money, and it is what you guys can relate to just a little bit. So let's look at some examples. Okay, this slide is just some formulas that you are going to need to know and that you will have to have memorized by the time we have the chapter test. So these are formulas that you need to memorize. Okay? First one is if you're compounding interest. So like if you put money into a bank, they give you an interest rate, and depending on how often they compound it or add to it or take the interest into effect, depends on how you would actually calculate how much money you have. So we've got some variables here in our top, there we go, in our top formula. So A is the amount you end up with. Like when you're done, how much money do you have in your bank account? P is the principal, which is how much you put into your bank account. R is your rate as a decimal. T is your time. A lot of times time is in years. And then E is your Euler's constant, and we'll be using the calculator for that. And you use this when you are compounding continuously, okay? And then the other one is if you're not compounding continuously, maybe you're compounding quarterly, so 4 times a year, monthly, 12 times a year, daily, 365 times a year. And then you would, if that was the case, you would use this formula down here, again, that you'll need to memorize. A is the amount you end up with, P is how much you put in, R is the rate as a decimal, those are all the same. N, in this case, is how many times it's compounded in a year, okay? So like, if, again, like I was saying before, if it is monthly, N would equal 12, because that's how many times. Quarterly. Quarterly would mean that your N would equal 4. Daily, if it was compounded daily, N would equal 365. Those are the most common ones I think that you'll see. So that's just making sure you know how to calculate with your N. So let's do a couple of examples. Okay, you invest $12,000 at an annual interest rate of 9%. That's a very good interest rate, okay? So if you invest $12,000, and it says you're compounding quarterly. So if we're using quarterly, that means N is going to be 4 times a year, which means the formula that we are going to use is our amount we end up with. This formula is from the previous slide, is your principal times 1 plus R over N to the N times T. Okay, so 12,000 in this case is how much you put in, that's your principal. 9% is your R, which is 0.09, it has to be as a decimal. 5 years, that's how long it was in there, that's going to be your T, so T equals 5. And it's compounded quarterly, which again means that N equals 4. So then you're just going to put those numbers into your calculator. You have 12,000 times 1 plus 0.09 over 4 to the N times T, which is 4 times 5. And you can put this all in your calculator exactly like this with parentheses and exponents and using the fraction button to make sure you're putting in the fraction correctly and things like that here. So you, on a test or something, you would, yes, need to make sure you show what this is, but then you can put that all into the calculator and you would end up at $18,726.11. Which means after 5 years of doing absolutely nothing but putting your money in the bank, you would go from $12,000 to $18,726. Okay, so take a second. I want you to figure out what it would be if you were compounded monthly. Do the exact same thing. Stop the video, put in your numbers, and see what you come up with. Okay, so if you notice, the amount you put in is still $12,000. The interest rate is still the same. However, now instead of only compounding it 4 times a year, you compounded it 12 times. So you'd have 12 here, and then it was still for 5 years. So if you notice, it makes a bit of a difference. The more often it is compounded, the more money you make. So only having it compounded 4 times a year above, you only made $18,726. By compounding it more often at 12 times, once a month, you make about $60 more in a year. So if we think about compounding continuously, remember continuously means that we are going to use what I call the PERT, P-E-R-T, formula from the previous page, and that means it is compounding continuously, which means if you can get an interest rate where it's compounded continuously, you're going to make more money. So let's look at how much more money. So again, we're going to use those same numbers. We're going to say we put in $12,000, and again, E is on your calculator. Your rate is still the same at 9%, and the time is still 5 years. So again, just like with the other one, you would need to show this step to get credit, but then you can just put it directly into your calculator. 12,000, hit that E button, and it'll give you E to the X, and then you would put 0.09 times 5 up in the exponent, and you would have $18,819.75. So in a year, by having it compounded continuously versus only 4 times a year, you'd make almost $100 more in a year in your interest. So those are kind of the real life examples of where you might actually see how some of this interest and exponential functions can actually be used with compounding. So another way, and this little blurb right here should be on the next page, we're going to look at half-life problems, which is, so, oops, my video went a little off there, but we're going to look at a half-life problem also. All right, so what a half-life is it's when you're using radioactive elements and things like that, or if you're finding the age of dinosaur bones or a lot of different things you could actually use half-life for. But the example we're going to look at is the half-life of radioactive radium. Okay, so radium is an element, okay, and its half-life is 1,599 years. What that means is that after 1,599 years, half of what you started with will remain. So if you started with 10 units of whatever it happened to be, however you would measure it, at 10, after 1,599 years, you would have 5, right? It takes that long to become half of what it originally was. So after another 1,599 years, a quarter of the original amount, which would be half of a half, and so on. So what it tells you here, it gives you a formula. Later on in the chapter, we'll be doing more with half-life and writing our own equations and things like that. But for right now, what it's telling you is that here's the formula for the half-life of radioactive radium, okay? So you've got 25 times 0.5 to the T over 1,599. Couple of questions, okay? What is the initial mass? So what is T equals 0? Well, that would mean you'd have Y. You have 25 times 0.5 to the T, which is 0, over 1,599. Well, logically speaking here, right, 0 divided by anything is just 0. Anything to the 0 power is just 1, so you would have 25 units left. Okay, or you started with, I guess. You'd have 25 units that you started with, because again, 0.5 to the 0 is just 1, so you'd have 25 times 1. Okay, how much is left after 2,500 years? Well, if we started out at 25, okay, we're at 2,500 years. Well, in about 1,600 years, we have half that. So we know our answer, just thinking logically, our answer should be less than 1,250, right? Because 12.5, because that's half of 25. Okay, so we know it should be less than that. I'm guessing probably even less than 10, but we can actually figure out how many grams are left. So we'd have that formula again, Y equals, we started out with 25.5. Now it wants to know when T equals 2,500. So we'd have 2,500 divided by 1,599. And again, if you just put that directly into your calculator, okay, you'd end up at Y equals 8.458 grams. Okay, so after 2,500 years, if you started with 25 grams, you would end up at 8.458 grams. As far as rounding goes, read directions. It says round 3 places past the decimal. WebAssign, make sure you're reading directions carefully so you know. And the other thing is pay attention to the problems. If it gives you a formula, all it's asking you to do is use that formula and plug the information in. So, good luck with your WebAssign.